Good morning, everybody. Hopefully you guys are doing okay. Hopefully everyone enjoyed the nice sunny weekend we just had. I spent almost all weekend outside just sitting on the lawn, taking it all in. If we could start with some green check marks, make sure everyone's with me, and we'll get going. Oh, it looks like I have chat off. Sorry, I don't know why that happened, but it did. All right. I want to get through a few things today. I want to talk a little bit about the midterm exam on Thursday. I want to talk a little bit about naming, which we left off with on Thursday last week or Wednesday. And I also want to talk a little bit about what I hope to get to today. So it's kind of where we're at. Oh, your social studies project. You're supposed to wait for a rainy day to finish that off. Don't tell Mrs. Ward I said that. All right, a couple things. In the course, I gave you guys those extra practice questions to go through with all of the naming stuff. And I have some solutions I'll post up at the end of today's class. So if you are going through all of those questions or you're looking at some of them, you're unsure if you've got them right or wrong, I have solutions for everything, and I'll put that up. The second thing is the midterm exam on Thursday, because you guys are all here on time this morning, and I'll give you a little breakdown of what it's all about. I'm in about a draft version of the exam that I wanted to make, and so far it's looking like about 25 or so multiple choice questions on chapters 1, 2, and 3. So the biology unit is think about it as 10 questions from each of the biology chapters. So 10 from 1, 10 from 2, and 10 from 3, all multiple choice. And then the second sort of section was the earth science section, and that's chapter 10, or unit 10. And there's about 10 multiple choice questions about earth science as well. So multiple choice has biology and the earth science. And then there's a few, I think like 4 or 5 chemistry multiple choice questions. And then there's a little bit of written. When I say written, it's not really written in the sense of like write out a long sort of answer. The written section is all on the naming we've been doing. So ionic, covalent, compounds, polyatomics, multivalents. So are you able to name a compound, and can you work the other way around? If you see a name, can you write down what the compound looks like? So that is the written section. It's about 45 multiple choice questions, and there is about, I think like 12 or so written questions. So everything's multiple choice except the chemistry section, all the naming stuff, it is the written. So that's kind of a breakdown for the exam. Hopefully that can help you a little bit in preparing for what that should look like. And again, on Wednesday this week, if you do have any questions about anything we've covered so far and you want to go through them with me, I'll be here from 1 till 3 for any extra help if you want that. So that's that. Does anybody have any questions about anything regarding anything we've been doing, anything we're going to do? I wanted to look at some of this naming stuff. When we left off, yeah, Anna, we can use the data booklet. This isn't loading. I will have a data booklet waiting for you there. I will have a test waiting for you. So all you need to bring is a calculator and a pen and a pencil. The calculator is there if you need it, but you probably shouldn't. So 4.3 is not on the test, that's right. The only section from chapter 4 would be the 4.1 and 4.2 on the midterm exam. So everything up to what we learned last day. So I'm going to go through a little bit of naming, just so we're kind of on the right track with that. When I get into balancing, probably in the second half of the block today, none of that will be on the exam, although it's kind of similar in terms of the information there. So yeah, you guys are on track. All right, so this is the extra practice sheets that I asked you guys to have a look at. practice naming and writing formulas. This is the last kind of booklet in that big, long 15 pages of extra practice. And what I wanted to do was go to the last page right here. And this is the very last page of all that extra practice. And the reason I wanted to come to this page is because it has everything kind of mixed up together. It has ionics, covalence, and there's polyatomics in there as well. And we didn't spend a lot of time looking at naming covalence or going from a name to a compound. So I wanted to do that a little bit before we get too carried away. And then I'll move on to today's material, the balancing. So this is naming and classifying compounds. The idea here is the naming rules change based on what type of compound you have. So it's important to be able to recognize the type of compound. If you have an ionic compound, how do we name that? If you have a polyatomic in there, how do we name that? If you have a covalent compound, how are you going to name that? So the rules change slightly depending on the type. And once we can recognize the type, we can be better prepared to name the compound. So the first one here, I just want to go through this first column, ionic, covalent, or polyatomic. Now, hopefully you guys remember the differences between these things. Now, technically, polyatomic ions form ionic compounds, but remember we don't change the ending of the polyatomics, so that's why we give them their own special sort of category. Because we're not changing the ending, the naming rules kind of change a little bit. So the first one here is VO2. I break out my periodic table, I look for V, and I see that V is vanadium, and vanadium is a metal. So as soon as I see a metal, I know I have an ionic compound. So I can put a little I in there for ionic. The next one, NO2. Nitrogen and oxygen are both nonmetals. So I don't have any metals here, so that makes this a covalent compound because I have two nonmetals. CR-Br. Cr is chromium and Br is bromine. So as soon as I have a metal, I have an ionic compound. CD-Br, CD is cadmium, it's a metal, it's an ionic compound. Then we get to SBr2. S is sulfur, Br is bromine, so we have two nonmetals, so this is covalent. The next one, Na2Cr2O7. As soon as I see this, and the next one for that matter, I can see that these things have more than three capital letters. They include three capital letters. So as soon as I see three capital letters, I know I'm dealing with a polyatomic. So these two are both going to be polyatomic. So I'll put P's in there for those. So I'm just going to stop there for a second. That kind of identifies those ones. Now we'll just name these and then we'll look at a few more. So the first one is V and O2. Now, the tricky thing here is V is vanadium, and vanadium is a multivalent, so it has more than one possible charge. So I need to figure out which one I'm dealing with. Now, it's bonded to an oxygen, there's two oxygens, and each one of those oxygens is going to have a charge of -2. So I have one oxygen at -2, I have two oxygens at -2. So that means the total negative charge is -4, and I only have one vanadium to balance it out. So it has to have a charge of +4. So when I have vanadium, I have to include the Roman numeral because it has more than one charge. And then I have oxide. So vanadium 4 oxide. The next example is covalent. Now we just touched on these at the end of last day, and I didn't get to spend a whole lot of time talking about them. And it's easy to confuse the rules, but when we have covalence, we name the leftmost first. So the leftmost is nitrogen. And if we only have one of the first element, we don't have to include mono. So we won't write mononitrogen. The next one is oxygen, and there are two of them. So I look at the little chart, and I remember that 2 is di, and then oxygen is oxide. So this is nitrogen dioxide. Hopefully that's okay. Do the next one. Again, I have chromium. Chromium is a multivalent metal, so it has more than one possible charge. This is where some people start getting the rules mixed up. They see the 2 after the Br and they want to put a di in front of it. This is an ionic compound. We don't use prefixes with ionics. So this is chromium. And then bromide. I need to decide what charge this chromium has. So bromine, Br, is always -1. I have 2 of them. There's 1 chromium, so it has to balance it out. So it is chromium 2 bromide. All right, I've been doing a lot of talking. How are we feeling about this stuff? Why don't you throw into chat maybe something that you're confused about or something that you want to see a few more examples of instead of me just standing here doing these problems. What's kind of the tricky stuff? You guys okay with covalence? You okay with polyatomics? You okay with multivalence? Or is there something you want to see a little bit more of? And I can just kind of pick them off the sheet. If everyone's good, I'd be happy to move on to today's material, but if we want a little bit more review on this stuff, I'd be happy to go through that with you guys. See a few of you typing. Definitely go over a few covalents. I'll pick off a few of those. When you put the di in front, I forgot about it. Yeah, so our covalents, they need the prefixes. Polyatomics and multivalence, yeah. So polyatomics, multivalence, and ionics, they're all ionic compounds. It's just a matter of remembering if the metal has more than one charge. And I would encourage you not to sit down and try to memorize the rules, not specifically you, Ava, but just in general. Instead of trying to memorize the rules, it's really good to just expose yourself to a lot of different examples. And the more examples you see, the more sort of the rules will just stick in your brain. You see 2 nonmetals, you use the nonmetal rules, things like that. So I'll do a few covalents, and then if everyone's okay with that, we'll continue on. So the next covalent here is sulfur and bromine, so SBr2. And sulfur is sulfur. So we have S, sulfur. And then bromine is bromide. But there are 2 of them. So on my data booklet, I look up 2, and 2 is di. So I'll put it in a different color, but you definitely don't have to. Just to kind of remind you. So this is sulfur dibromide. There's another covalent down here a little further. N2O3. This will be a good one to do. So because the first element in this example is nitrogen, and there's more than one nitrogen, we have to use a prefix for the first element. When there's only one of the first element, we don't start it with mono. If there's one of the second, we do use mono. But in this case, it has 2. So I name the first element first. So this is nitrogen, nitrogen. And then I have oxygen, which is oxide. And then I put my prefixes in. How many nitrogens do I have? There's 2. Well, I know 2 is di. So I have dinitrogen. And then I have 3 oxygens, which is tri. So I have dinitrogen trioxide. And yes, Abby, they always end in "ide." There's no exceptions to that rule. Covalents will always end in "ide." See if I can find a covalent. There are no covalents with only 1 in the second. Maybe I'll go down here to this oxygen and chlorine. We're used to seeing oxygen come as the second element in a covalent, but in this case it just happens that chlorine's further to the right on the periodic table, so we name oxygen first. So this is oxygen, and then chlorine is chloride, and then I put in the prefixes. So I never start with mono, but I always have to name the second one, even if there is one. So this is oxygen dichloride. Taylor, for sure I can do a polyatomic. Let's do the ones up at the top here. Na2Cr2O7. So I look at that, I kind of get a little flustered. There's an Na. Is the Na with the Cr? Is the Cr with the O? How do I know? Well, remember there's only one polyatomic that will start a compound. So generally speaking, the first element is going to kind of hang out by itself, and then your polyatomic is going to be the second two elements together. So if I look on my polyatomic sheet, which is page 5 in your data booklet, I look for Cr2O7, and that's called dichromate. It's about the top third there. So Na is sodium, and Cr2O7 is called dichromate. So sodium dichromate. I don't change the ending on chromate. I leave it 8 because it's a polyatomic. I don't want to change it to "ide" because that'll confuse me. So this is sodium dichromate. Let's see if I can find a multivalent with a polyatomic just to do one tricky one. I don't see any on here. Nope, there aren't any. Let's do this polyatomic right here, and then we'll move on. Li2SO3. So I see 3 capital letters, the L in lithium, the S in sulfur, the O in oxygen. And again, the metal is almost always going to just be by itself, and then you're going to have the polyatomic as the second two stuck together. So Li2 is lithium, and lithium happens to only have 1 charge, so I don't have to worry about Roman numerals. And then SO3, look it up on my sheet. Down at the very bottom, it's called sulfite. This is lithium sulfite, which looks really similar to the next one down below it here. What makes these two different? Well, if you look really carefully, this one has SO3, this one is SO4. So this is lithium. And then SO4 is called sulfate. So lithium sulfate is different than lithium sulfite. That's why the endings are very important. Ides, ites, and ates, they all mean different things. So you need to keep it straight in your head, and that will help you out a lot. So the answers to all of these are going to be up at the end of the class. I'll unhide them. So I encourage you to go through as many of them as you can. Next class, if you guys have more questions about them, at the beginning of class, I'd be happy to go over them. So do as many as you can. Check your answers. Please, please check your answers. And if you run into problems, if you're getting something wrong or there's something that you're continually getting wrong, ask you about it next day. If you just make a silly mistake, well, that happens. Just try to take your time and do your best, and that's all we can ask for. So that's kind of naming. I'll leave it there for now, and I'd be happy to go through more questions next day once you guys have a chance to maybe try a few more and then go back and look at your solutions, make sure everything's good. I had sent you guys a message on, Friday's course, or maybe Thursday morning. We didn't have class Friday, but maybe Thursday, and I said, we're going to be doing this worksheet called Counting, and I asked you guys to download it, and hopefully you had a chance to do that. If you don't, again, you can just kind of work through it with us today, and away you'll go. So this is what I want to talk about right now, and I have it loaded in here. Sheet's called Counting the Atoms. Now today we're going to start balancing equations, which is kind of the... Oh, you didn't get it, Taylor? I'm sorry. If you didn't get it, it's there. You could just even write these down. They're not terribly difficult or terribly long to write down. So if you had some blank paper, you could just do this as you see it come up. When we're doing balancing, if you think about how we started with the Bohr model and protons, neutrons, and then we kind of said, okay, if Bohr models get kind of close together, this is how they bond ionically. So they transfer electrons, they stick together. So then we started talking about, well, we don't have to draw the Bohr models all the time. We can just use the charges in the periodic table. We can form compounds. So we can see how these things stick together. Now what we're going to do today is, what happens when we stick these compounds close to one another? Will they react with one another? Sometimes they do, and sometimes something new is produced. So the chemistry unit's kind of interesting how it gets kind of built up. You do the compounds. We're going to talk a little bit about balancing today, and then we're just going to kind of build on that idea of balancing. The next chapter we're going to do is chapter 6. It talks about types of reactions, which takes the idea of balancing one step further. So everything you learn in chemistry kind of builds on itself until you get to the end in chapter or unit 6, and it all kind of comes together. So we're going to start with some really basic examples that you're going to be like, Mr. Borden, why are you even bothered with this? And then we're going to get into some more complex things. If you can kind of get how this works, then the balancing will be hopefully a little bit more straightforward for you, because it can get very tricky. But for now, if we can master this stuff, we'll be doing okay. So the idea here is to count how many atoms we have. So if I have a compound like sodium chloride, Na and Cl, it's important that I can recognize how many Nas are there and how many Cls are there. So what I'm going to do, and what I encourage you guys to do as well, is get into the habit of doing this. And we will do this for almost all of the balancing type questions we have. So Na and Cl. How many Nas are there? How many sodiums are there? Well, what I do is I always look to the back and I look to see if there's a subscript written after it. Now, if there's a subscript like a 2 or a 3, then that means there's 2 or 3 of them, and I can write that down. If there's nothing there, I know it's just 1. So for sodium here, there's nothing written after it, so I know I have 1 sodium. And same thing with chlorine. There's nothing written after it, so I have 1 chlorine. The next one here is we have a hydrogen, we have a sulfur, and we have an oxygen. And we want to count how many of each of these things we have. So H, I look at first, has a little 2 next to it. So how many hydrogens do we have? We have 2. This is where things kind of get a bit tricky. I have this SO4 molecule. Most of you will be able to recognize that as a polyatomic. Now, do I have 4 sulfurs or do I have 1 sulfur? And how many oxygens do I have? This is where things kind of, get a bit tricky. What's written next to the sulfur? What's down here? Well, there's nothing. So how many sulfurs do I have? I have 1 sulfur. I don't have 4 sulfurs, I only have 1 sulfur. The oxygen has the 4 next to it, so I have 4 oxygens. All right, I'll do the next couple here and then I'll give you guys a few to do. This next one, I have a nitrogen, I have a hydrogen, and I have a bromine. So nitrogen has nothing next to it. I have a 1, hydrogen, 4, bromine, 1. All right. I've identified the elements for you guys. I want you to just take a minute. I won't even put a timer up, but just take a minute to see if you can count those. And how about for the fun of it, everyone throws number 7 into chat just to see if we're doing okay. See if everyone's on the right track. If you're feeling brave, so just go ahead and kind of plug away at those. Just count them real quick. And then if you don't mind throwing 7 into chat, we'll see what everyone comes up with and we'll see how we're doing here. All right, we have 2 brave souls with solutions to number 7 in. They're both looking the same. Does that mean they're both right, or did they both make the same mistakes? I don't think we can argue with 3 people. They must be right. And you guys are, in fact, right. So H3P104. We're starting really basic. And the reason we start really basic is kind of like the ideas when we were in math. If you can do a really basic example, when things get more complex, maybe you can figure them out based on the really simple examples. So thanks, Taylor Abiana. Yeah, you guys were all right there, which is great. So those were really basic, kind of simple ionic compounds. What if we kind of ratchet things up a notch and we throw in some polyatomics with brackets? If we have more than one polyatomic group, it's important to put them in brackets. If we don't put them in brackets, the numbers get all mixed up. So let's look at a few of these. We're going to do the same sort of process. We're going to identify all the elements. So I see I have Ba, I have an O, and I have an H. Even though the oxygen and hydrogen are polyatomic and they're bonded together, we're going to count them individually. Does anyone want to take a stab at this one? See how you're doing? What do you think in terms of the numbers of the O and H? The barium's pretty straightforward. I mean, there's nothing after it, so that one's not too tricky. But what about the oxygen and the hydrogen? How are we going to count those? What does the brackets really mean? Ba1O1H1. If there's one of each of these, what is the 2 meaning behind it? The brackets are helpful because they remind me of how it is similar to the math multiplication process. You know what? It's exactly the same as I called it feeding the chickens. And when we're counting these things, you want to think of it as the exact same process. If there's something outside of the brackets, everything inside the brackets gets the 2. It's exactly the same as feeding the chickens. So what this really means is if I have this molecule, I have Ba, and then I have the OH, but there's a 2 next to it. That means I have 2 groups of the OH. So I have 1 barium. I have 2 oxygens and 2 hydrogens. So that's what the 2 is telling me. Anna, you got it. I like the accent on the E too. That's nice. I hate it when my keyboard does that to me. I'll be typing and I'll throw in a question mark and it gives me some fancy letter in like the French character set. I don't know why it does that. Just keep you on your toes, I guess. All right, so the barium and the hydroxide, or the BaOH, we got that one. The next one, again, is perhaps a bit tricky. We have the Ca. There's one group of that Ca. It tells me there's two groups of PO4. So I have a group of PO4. I have another group of PO4. So I have that one calcium. And then how many phosphorus do I have? Well, I have one in the first group of PO4, and I have another in the second group of PO4. So I have 2 phosphorus. How many oxygens do I have? Well, I have 4 here, and I have another 4 here. So my oxygens are 8. Bit tricky. Anyone want to take a shot at the next one? We have aluminum, we have sulfur, we have oxygen. Couple people going for it. How did I get 8? It's a great question. The 2 after the PO4, so there's 2 down here, means I have 2 of this entire group. I have 2 of this PO4 group. So if I write down PO4 once, that's the first group. So I have CaPO4. And then the 2 means I have 2 of whatever's inside the brackets. So if I have 4 oxygens here, I have another 4 oxygens there, which gives me 4 plus 4, and that gives me 8 in total. So sometimes it's helpful to just write out that polyatomic more than once to figure it out. We can do the same thing here. With this SO4, how many groups of SO4 do I have? Well, there's a 3 after it. So that means I have 3 groups of SO4. So I look after the aluminum, I see a 2, so we're probably okay with that. The sulfur, how many sulfurs do I have? Well, I have 1 sulfur here. There's my second sulfur, and there's my third sulfur. I have 3 groups of sulfur. And oxygens. I have 4 here, I have another 4 here, and I have another 4 there. So 4 and 4 is 8, plus another 4 is 12. And Taylor and Anna, you guys are both right, which is good. All right, the last one here, Mg. There's nothing after the Mg, so I know it's a 1. The N, there's 2 groups of that NO3, so that means there's 2 nitrogens. And then there's 2 groups of 3, which is 6. If you kind of want to think of it as multiplying these things together, that'll work. So 2 times 3 gives me 6, and then 2 times 1 gives me 2. For those things. So in terms of multiplication, it's going to work. It's exactly like feeding the chickens in math. So same sort of process. These are kind of the more tricky ones. There's one more tricky example beyond this. Let's do these ones together real quick, and then we'll do the last set, which are the most challenging. So we have Cu, we have N, we have O, Mg, C, H, O. All right. Let's give you guys a second to do those ones. See if you can count them up. 6 and 7 are intentionally tricky, which is good. Taylor, it's looking like you've mastered these already, which is excellent. 6 and 7 are tough though, so make sure you take your time with them. What are we thinking? Taylor's got it. Does anybody else agree or disagree with Taylor? We'll put Taylor out there today. What do you think? Those last ones. Taylor, you're right. You're doing great. Good stuff. And I'm hoping everyone's fairly comfortable with this. We'll start pretty basic, but obviously things can get trickier as we kind of plug away. So N3H12P1O4. Excellent. You guys are on the right track. So let's challenge you a little bit further here. Ratchet things up a little bit higher. Now, we haven't discussed balancing. And Abby, this is kind of getting back to the question that you asked earlier that I kind of skipped, was, hey, what's the difference between the balancing we've been doing and the balancing we're going to do? And the stuff we're going to look at today is taking chemical equations and balancing the elements on either side of the equation, whereas the compounds we were building before was just putting two things together and kind of making sure that their charge is balanced out. So today we're going to introduce an idea in which we put a big number in front of a compound. It's called a coefficient. And what that big number does is it identifies how many of that group of atoms we need to balance everything out. So without talking a ton about how that idea is going to work, if we just kind of take it at face value just in terms of a number, what does that do to these compounds? So let's look at a few of these, and I'll kind of explain how it works, and then we'll do some of the examples together. So you can see here, there's this giant 3 in front of the H2O. That's not a typo. What that 3 means is that there are 3 groups of H2O. So if I want, just like I was writing those polyatomics before, I could write this out 3 times. H2O, H2O, and H2O. So what that 3 tells us is that you have 3 of that H2O group, or that water molecule. So I break it down just like I did before. What elements do I have? I have hydrogens and I have oxygens. How many H's do I have? Well, I have 2 in this first group, I have 2 in the second group, and I have 2 in the third group. So there's 2, 4, 6. And oxygens, I have 1, I have 1, and I have 1 for a total of 3 oxygens. All right, so that's a basic example that'll get us warmed up here. What if I put a 4 in front of the second group? What happens there? Now, I guess there's kind of 2 ways you can look at these things. You can think about them in terms of math, like some of you are, where that 4, if you want to maybe put these things in brackets and feed the chickens, kind of like we did in math, that sort of concept will work. Or you can think about writing this out 4 times. So you can get Fe2O3, 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 and Fe2O3. So I identify the elements present. I have iron and I have oxygen. How many irons are there? Well, I have 2 in the first one, I have 2 in the second one, I have 2 in the third, and I have 2 here. So 2, 4, 6, 8. Taylor's right. And then oxygens. How many oxygens do I have? Well, I have 3 in this group, 6, 9, 12. So maybe I'm taking you too slowly through this, but I can't stress it how important this counting stuff is. Now, these ones are pretty straightforward again, but they're going to get a lot more difficult. So why don't you guys, because I think most of you well, those of you who have written into chat seem to be doing okay. I'll give you a couple minutes. I won't put a timer up, but just a couple minutes to see if you can go through the rest of the questions here all the way down to number 9. And I'll just leave them up on the board here just in case you don't have the sheet downloaded. And even if you have a scrap piece of paper next to you, if you're just writing the elements down and the numbers just to check. I guess one thing I should mention about this is, generally speaking on tests and exams, there won't be, well, I shouldn't say there won't, but it's not likely that you're going to see a question that says, hey, how many of so-and-so element are there? That's just not kind of one of the learning sort of outcomes that we have you guys do. It is built into the idea, though, of you guys balancing, which we're going to do today. So if you aren't unable to count, then balancing is going to be really difficult for you. So there are 9 questions here. I did the first 2 for you, so there's 7 left. I just want to give you guys a second or 2 of time to go through the 7 that are left, and then we'll check our answers. So have at her, and I'll just kind of hang out here and do a little dance while you guys do this stuff, and then we'll come back and check, and the last few are difficult. So take your time, it's no rush, and we'll check them out here in a second. All right. I'm not intending to rush you guys. If you're not done, that's okay. If you haven't looked at the last couple, maybe 7, 8, or 9, if you're working slowly through these and you want to jump down to those and see how those go, what's really great is that these questions, like 7, 8, 9, these are as difficult as these get. There's no kind of step beyond this that gets more difficult. So if you're feeling confident with this stuff and you're going through these and you don't seem to have any problems, and then you get to 7, 8, 9 and things are looking great and you're getting the same answers as me, that's good. That's as tough as these get. So if you are okay with those last ones, then you're doing good. And one other thing is, don't be afraid to actually write down the groups several times. So if it says something like 2AL, 2SO4, and 3, write 2 of those groups down. And if there's 3 groups of that SO4, write those down 3 times until you have everything written, and then you can just go through and count each thing. So there's no shame in writing these things down several times, like writing them out, expanding them with all the 2s and 3s and the coefficients and everything, because it's really important that you understand how many of each thing are there, which makes your life in terms of balancing a lot easier. A few of you are saying, oh, the last ones are tricky, I'm having troubles with them. I want you to take a go of writing them down. Just make sure you write something down. If you're confident in it, that's great. If you're not, that's okay too. It's okay to make mistakes. This is the first time you guys have ever seen this stuff, so can't expect you to be perfect right from the start. I make mistakes on these from time to time, and it happens. They're big, they're long. Sometimes you get these really complex things happening, so don't be afraid to make a mistake here at the very beginning. We'll do lots and lots of practice with these things. You'll see lots of examples. And this is your first experience with them. So we'll put the answers up, and hopefully you can check mine. And if you have something different than me, then say, hey, Mr. Bourne, is it possible that this is this? Because I went through these really quickly, and they are kind of complex. But I'm hoping I did an okay enough job. You guys can check your answers against mine. If you have questions, even after you've seen my answers, like, hey, where did you get 24 oxygens for number 7? I encourage you to write something in chat so we can go through them. Maybe I'll write it down a few times and expand on everything, and maybe then you'll be able to see where those numbers are coming from. Or if you're doing great with these things, in chat just say, yeah, things are looking good, Mr. Borden, or I'm okay, I'm happy with my answers. And that way I kind of know you guys are on the right track with this stuff. So if we, how did you get number 24 oxygen for number 7? All right, that's fair question. Pretty good. Does that mean you got them all right, or does that mean you're kind of like getting there? I'll do number 7. I'll write it all out. And number 6. Okay, I'll do 6 and 7. And hopefully that'll maybe alleviate some of the issues that, and of course I didn't show any work or do anything, but I want to make sure you guys are okay. So let's look at 6 and then we'll look at 7 and then we'll move on. So I'll do number 6 on the left side here. There is 3 groups of this Ba, OH, 2. So I'll write down one group and another group and another group. All right, so there we go. I have those 3 of those groups. So the barium, the Ba, is pretty straightforward. I have 1 here, I have 1 here, and 1 here. Carbons, 4 carbons, 12 hydrogens, 12 hydrogens. Now I have 10 oxygens and 2 oxygens. If I put a 5 in front here now, that gives me 10. So 4, 4, 12, 12, 10, 10. So combustion reaction, super tough. The most difficult you'll encounter will be these combustion type reactions. I would apologize for the notes being so difficult, but I didn't make them, so I don't know what to tell you. Let's look at the learning guide, and let's look at a few really easy examples to get started with. Probably should have done them in the backwards order. Now I know better. Okay, so the learning guide, we're on 4.3. You guys have gone through all of that. Those are the 3 examples we just did. I'll get to this writing word equation stuff in a second. But let's look at a few of these examples. I don't know that they would expect you to start with those. I think it's just the ones that they included, so whatever. We'll get over it. All right, let's do the same process right out of your learning guide. The T-chart's already drawn for you, which is really nice. So if I have Mg, H, and Cl as reactants, you guessed it, I'm going to end with Mg, H, and Cl as products. Law of conservation of mass, if I start with it, I end with it. I start with 1 magnesium, 1 hydrogen, 1 chlorine. I end with 1 magnesium, 2 hydrogens, and 2 chlorines. Now, if you picked up anything from what I just explained, let's see if you can try this one. Start at Mg. You have 1 on the reactant side, you have 1 on the product side. So that's balanced. They've already given you the spaces for coefficients, which is nice. So I start with 1 hydrogen. I'm ending with 2 hydrogens. That's not going to work. So if I need to end with 2, what I'm going to do is I'm going to put a 2 here. That's going to change my hydrogen from 1 to 2. And it's also going to change my chlorine from 1 to 2. Now I can go and check it out. I have 1 magnesium, 1 magnesium, 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines. So the only thing I needed to do here was just add a 2 in front of the HCl, and that balanced everything. That was the example I should have started with. In hindsight. Hindsight's 2020. How do we feel about that one? In chat, now that I've confused you with 3 really hard examples, what about the first example here? Are we okay with that? Everything seemed kind of acceptable there, nothing too drastic. No smoke, no mirrors, no exceptions to the rules. Make me feel a lot better if you guys were okay. Kind of super easy. Good, at least it feels now that we didn't have that. All right. I'll take the fall for this, the mess that I led you into. So let's do the next one, and then maybe I'll step back and give you guys some time to work on these. So the next one, I have a magnesium Mg to start and a nitrogen. If I start with magnesium and nitrogen, I must end with magnesium and nitrogen. Those are the rules. All right, let's count. I started with 1 magnesium and 2 nitrogens. I end with 3 magnesium and 2 nitrogens. Okay, I need to balance my magnesiums first. So if I have 3 on my product side here, I need to start with 3 on my reactant side. The only way I can do that is adding a 3 in front. I can't put a 3 down below. Remember, we can't add subscripts, we can only add these coefficients in front. So instead of having 1 magnesium, now I have 3 magnesiums. So 3 on this side, my reactants, 3 on my products, 2 nitrogens, done. Now, sometimes people will put in ones here, which doesn't change anything, but it just allows you to put in a 1. I won't, I'll leave them blank, but in some, I don't know if the answer key has ones, it may. Sometimes that's a way to like hold a place. So you might see ones, you might not, it doesn't change anything. Okay, so those are the first two. I'm gonna skip the third one because that's a pretty straightforward one. And maybe look at the fourth one here. Cl2, 3. Yeah, let's do this fourth one. BiCl3, H2S, Bi2S3, HCl. So this is the fourth one. I'm starting with Bi, Cl, H, and S. I have to end with Bi, Cl, H, and S. If I start with it, I must end with it. How many Bi's do I start with? Well, I start with 1, and I end with 2. Cl, I start with 3. H, I start with 2. And S, I start with 1. Do the same thing on the product side now. 2 Bi's, 1 Cl, 1 H, and 3 S. This is why counting was so important. If you are not good at counting, balancing becomes that much more challenging. So if you need to go hone your counting skills, do that first. All right. I started with 1 Bi, I end with 2, so that's a problem. So what I'm going to do is I'm going to put a 2 here. So that changes this to a 2. But because I put a 2 in front of this whole compound, I have two groups of the Cl3. So I actually have 6 chlorines now. How's that working, guys? Are we good? Sorry, my microphone died mid-class. Good, perfect. Sorry about that. The batteries were low. We were hoping we could make it. Turns out we couldn't. Cool. All right, so where I left off was that I changed the chlorines over on the product side to a 6, which also changed the hydrogens to a 6, which is okay. We can deal with the hydrogens now. Now, if I have 6 to end with, I have to start with 6. Now, I can't put a 6 here because that would be 6 groups of 2, which is going to give me 12. And I don't want 12. I want 6. So 3 times 2, 3 groups of 2 gives me a 6. But that also changes the sulfur to a 3, which turns out to be what I wanted. So just kind of one of these situations where everything kind of worked out. So 2, 6, 6, 6, a 6, a 3, and a 3. Everything's balanced. What are we thinking here, guys? Do you want me to do 1 or 2 more and then give you guys some time, or you just want to have some time to work on this stuff. Let me know what you're thinking. Let me know how you're feeling. And then we can go from there. Ava, I knew you would like these. They're very logical. They're systematic. I really like them too. I think they're fun. And you'll get into some tricky ones later in the learning guide that don't just work out nicely, and you got to kind of think outside the box a little bit. Yeah, let's do that. That's a good idea. Maybe we'll put up it's 10 after. We'll put up 10 minutes. Let's go with 8 minutes so we don't keep you too long. 8 minutes, that'll give you guys some time to just do a few of them. Just do as many as you can in 8 minutes. And then I'll come back and I will go through them. So I'll try to do the first 2 pages of these examples, and then you guys can check your answers against mine. So we'll put up a timer and we'll meet you guys back here in 8 minutes. Thanks. them. All right, guys, welcome back. All right, gave you some time to go through a few, see how you did. I kind of scrolled back up to the one I skipped, and it turned out that it was pretty straightforward to balance. So that was that one. Remember, the answers to these are in the back of your learning guide as well. So if you're going through and you want to check on your progress, that's a good thing. So there's those ones. I did those. I also did this one for you. So a blank, a 2, a blank, and a 2. And then I did a couple on this next page as well. A 3, a 2, and a blank. A 2, a 3, a blank, and a blank. One thing that can happen with these is you end up getting an answer that's double or triple the lowest one. So just for like an example, if you had 4 blanks and you had something like a 2, a 2, a 4, and an 8, that can be reduced down. Just like ionic compounds, we can reduce them. So if you divided everything by 2, you'd get a 1, a 1, a 2, and a 4. So if you have an answer that's double something I have or triple, if you reduce it to lowest terms, you'd be okay. That being said, on an exam, the lowest terms answer will always be there. So if you had something that had, was double or triple the answer, it's right, but unfortunately, you've just doubled it. So just something to be aware of. Even though you've balanced everything correctly, you've just got 2 or 3 times the simplest possible solution. So when you guys are looking at some of the answers I have here, then if that happens, then you got it right, but you just need to reduce at the end. So something that'll just come with a little bit of practice and time. If you put a 2 in front of the CaCO, would the 2 be? Would the O be 2? Ca. Yes. Are you telling me I didn't finish this one? Ca is 2. Okay, so I didn't finish this one. Let's go back. O is 2 and 2. That was good. Ca is now unbalanced, so I'm going to put a 2 here. Changes that to a 2. But that also changes my C's to a 4 plus 1 is 5. So I don't want that anymore. I want a 5. So 252. And I think that's what Abby was saying as well. 2521? Perfect. That makes more sense. Hopefully me not finishing it or not getting the right answer. So these, yeah. It's important to try to do these in pencil because sometimes you have to go back and erase numbers. And if you're doing it in pen, it gets really messy. So I don't insist on you guys using pencil, but this is kind of one of those things where as you're going through, you'll have to go back and erase things in terms of your coefficients out front. So get in the habit of using pencil. I'm gonna maybe leave it there for now. I'll go through some more of these answers next day. I'll go through any more compound questions you guys had next day. And then if anything comes up for the provincial exam that you want me to go through, I'd be happy to go through that stuff as well. But it's important that you guys try these, do your best. If you get stumped on a few of them, that's okay. We'll go through them next day. But at least try them before next day so we can make sure you guys are on the right track. Technically, that's kind of the end of Unit 4 as well. There's nothing else to do. I do want to spend some time on going from word equations to compounds or skeleton equations and then balancing. It does take a ton of practice and it's tricky, and that's the last slide on the learning guide there that I haven't done yet. So we'll do that next day and we'll look at doing some of those. I think I'll also get an additional sheet because just looking at the learning guide, there aren't any questions that go from word equations into chemical equations and then balancing. So that's something we'll need to do. When will the learning guide be due? Good question. I don't know. I would love it if you guys could finish it off for the weekend, but I think studying for the midterm is really important. So I'm going to put the midterm as being more important than this Unit 4.3 stuff we just did today. So I'm thinking I'm going to... We'll start talking about this Unit 4 stuff maybe after the weekend. So don't worry about any of it for before the weekend. I would love it if you guys focused on the midterm for now, going back, reviewing some of the biology, reviewing some of the earth science, and the first 2 sections of Unit 4. And then we'll talk about this being due maybe Monday, Tuesday, Wednesday next week. We're going to jump into Unit 6 from here. We're going to skip 5 for now. And Unit 6 is more of this balancing, more of the same. So, you know what I'm going to do is, let's scratch the Unit 4 test. I still want you to hand in your Unit 4 learning guide, but we won't do a test on Unit 4 because the stuff comes up again on Unit 6. So that'll make your lives easier. You guys have this midterm. I want you to focus on that. So there'll be no Unit 4 test. I'll put some Unit 4 questions on the Unit 6 test to make it a little bit longer. Just the balancing stuff, not the compound stuff. So that makes sense. Thinking on the fly here. So if you guys have any questions about that or anything else, we can deal with it next day. Next day is on Wednesday, which is the day before the midterm. We'll go through some compounds. We'll go through balancing and anything that you have in terms of midterm questions. And the midterm will be your Unit 4 test. Yeah, there's a bunch of questions on there from Unit 4, so that'll be good. I don't need to test you guys on that stuff twice because it's fresh in your minds. So that's where we'll leave it. So thanks, guys. And if you have questions between now and next day that come up about balancing or anything, send me a message. I can probably help you out. If not, we'll go through a bunch of more questions next day, and then we'll start Chapter 6 after the end of this week, so starting next week. So thanks, guys. We'll see you on Wednesday. So I have 3 of the bariums. So hopefully we're okay with that. See if I can get rid of that without erasing everything. There we go. Now I have this OH group, and I have 3 of the OH group. So I have 3 of the OH group, and then there's 2 here. So this really means that each time I have this, I have an O and an H, an O and an H. And then here I have an O and an H, and an O and an H. And this 2 means I have an O and an H, and an O and an H. So how many O's do I have? Well, I have 1, 2, 3, there's 4, there's 5, and 6. So there's 6 O's, and the process for the H's is exactly the same. So I have 6 H's as well. So I don't know if that confused you more or helped you more, but there are 6 O's and 6 H's because we have 3 of the BaOH2. For each one of the OH groups, I have 2 of them, so 2, 4, and 6 in each of them. I'm gonna erase that, and then we'll look at 7 a little more closely. Yeah, I mean, these things are tricky, right? They get a bit confusing. Let's look at 7. So I have this Cu group, and then I have this NO3, and then there's 2 of them. And I have this 4 times. So Cu, NO3, 2, Cu, NO3, 2, and Cu, NO3. With a 2. So usually the first element, the metal, is pretty straightforward. If I'm counting coppers, I have 1 copper, 2 coppers, 3 coppers, 4 coppers. So that one hopefully didn't stump you. I have a feeling the N's and the O's are going to stump you. So for each one of these groups of NO3, I actually have two of them. So that means I have NO3 and NO3. So essentially each time I have this blue thing written, that means I have two N's. So there's two N's in this first one, there's two N's here, there's two N's here, and there's two N's here. So 2, 4, 6, and 8. That's where I got the 8 from there. Get rid of all the red 2's here. The last one is the O's. So for each O group here, I have 2 of whatever's inside the brackets. And inside the brackets, I have O3. So that means I have O3 and O3. That's what the 2 is telling me here. So each time I've written this thing in blue, I really have 6 oxygens. So I have 6 oxygens here, I have another 6 oxygens here, I have another 6 oxygens here, and I have another 6 oxygens here. So in total I have 6, 6, 6, and 6 is 24. So that's where the 24 came from. For my oxygens, or I can take a giant leap back, get rid of all of this, and I can think of it in terms of math, if I would like. So if you want to put brackets around everything, this is like 4 groups of that. And then I'm going to multiply the 4 by the 2. And then once I've done that, I'm going to have 4 times 2 is 8. And then I'm going to multiply everything inside the brackets by the 8. So that's where I have 8 nitrogens come from, and then 8 times 3 gives me 24 oxygens. So if you want to think of it in terms of groups, that'll work. If you want to think of it in terms of math, multiplying each of these things, that'll work as well. So whatever works the best for you in your brains, that's how I encourage you to look at it. There's no way that is more correct than the other. For 8, you got 14 oxygens. So just in terms of math, I'm going to go 2 times 3. 2 times 3 is going to give me 6. And then I'm going to multiply that 6 by whatever's inside the brackets. So I'm going to get 6 sulfurs, and 6 times 4 is 24 oxygens. So 2 times 3 times 4 is 24. And again, if you're looking at these and thinking, wow, when am I going to ever understand this stuff? This is the first time you've ever seen it. So we're going to have lots and lots of examples of this to come. And we're going to start really basic, and we'll get a little bit more complex. And hopefully you kind of pick it up after a while. So these last ones are very complex. Don't think that they're all going to look like this. These are kind of the most difficult you're going to see. So if you're okay with that, then you're doing okay. So if you got the first sections, there's 3 sections on this sheet. If you got the first 2 sections, you'll be doing fine. This last section, with a bit of practice, you should be okay. So that's it for counting. I know there's nothing in the notes about counting. It's just something that, we hope you've mastered, but I really think it's important that we take a second to kind of master this stuff before we look at balancing. That kind of is maybe a good natural break right there before we can jump into the balancing type questions. So maybe we'll take a 10-minute break here, and we will get into the balancing notes after the break. It's just, I don't want to take a break in the middle of balancing. So I think you guys earned a break. We're going to take 10 minutes, and after those 10 minutes are up, we'll come back. We'll talk a little bit about balancing, and we'll get into the notes. So if you don't have the notes printed off, or I guess you would, because all of section 4, but we're going to start 4.3 in 10 minutes. So we'll see you guys back here in 10 minutes. Thanks. All right, guys, welcome back. If you wouldn't mind, give me a green check mark, just so I know you're with me, alive and well. And then we'll do some notes here. This is continuing on section 4.3 when you're learning guide. And again, I don't love this learning guide, chapter 4, unit 4 stuff, but it is what it is. Splendid, thanks guys. All right, so balancing chemical equations. We're gonna take a lot of stuff we've already looked at. We're gonna take some of the counting stuff. We're gonna put it all together and come up with some balancing. So chemical reactions take place all around us all the time. And I think in grade 8, you spend a bunch of time talking about the difference between chemical changes or physical changes. And everything we're going to deal with here is going to be chemical change. So if you recall the definitions of chemical changes where new substances are created, sometimes you have like the production of heat or light, sometimes you have color changes, and these are sort of typical examples that some sort of chemical change has occurred. So there's some basic vocab we'll talk about, and we have these things called chemical equations. They're almost identical to math equations, as they're really, really similar. Instead of numbers, we're dealing in elements. So anything on the left of an arrow, the arrow is kind of like the equal sign. Anything on the left we call the reactants, and anything on the right we call the products. So reactants are what you start with, products are what is produced. That's where the word product comes from. The arrow shows the direction of the reaction, and you'll see different types of arrows depending on different types of reactions, but mainly in chemistry, science 10, you have a one-way arrow, reactants on one side, products on the other. And then we have these numbers in front that you'll see we call coefficients, and we actually looked at those already when we were talking about counting. So there's different types of chemical equations you'll see. You can see things like this down here. This is a word equation. Nitrogen monoxide plus oxygen is nitrogen dioxide. So the arrow in math, if we had a mathematical equation, when you see the equal sign, you say something like is. So x is 2. Which means x equals 2. In chemistry, you can replace the arrow with something like reacts to produce. That would make sense. So in this case, nitrogen monoxide plus oxygen reacts to produce nitrogen dioxide. That's how we would say this word equation. We can, because you guys are amazing, you can take those word equations and you can convert them into chemical equations or symbolic equations. So nitrogen monoxide, you know what that is. Nitrogen, you see the mono, and the oxygen is nitrogen monoxide. This is NO2. Just ignore the 2 for now and the 2 over here. We haven't talked about how those come about. Oxygen is oxygen gas, like we're breathing. That's O2. We'll talk about why there's a 2 here in a second. And then nitrogen dioxide is nitrogen, and then O2 is dioxide. So you guys have the skills to take a word equation and convert it to a symbolic equation. And that is the most difficult thing you will do in this section, is take those words and convert them in there into the symbolic equation. So this is just kind of getting our toes wet, general ideas, some basic vocabulary. We haven't really talked about balancing. So when we talk about balancing, we're talking about the big numbers in front of the compounds that we've already formed, and we call those big numbers coefficients. And when we put a big number in front of a compound, it says how many of that compound are there. So we've already looked at this counting stuff, and it tells us how many are there. So we'll get into that here in a second. What's the G for? What's the L for? What's the S for? What's the AQ? These are all states of matter. Sometimes chemical equations will have the G, and the G next to it, and sometimes they won't. It just depends on who's writing the chemical equation. Generally speaking, if we're writing these things in kind of shorthand, we won't put the states of matter in, but sometimes we will put the states of matter in, or you'll see them with the states of matter in there. And solid, liquid, gas, these ones are pretty straightforward, S, L, and G. The only one you likely haven't seen before, it doesn't make a ton of sense, is the AQ, which means aqueous, which is just a fancy chemical way of saying, hey, we dissolve that stuff in water, and that's it. So typically speaking, a lot of times when we do chemical reactions, you'll take some sort of solid, and solids, when you put solids together, they don't mix very well, just because of surface area. So sometimes what we'll do is we'll dissolve it in water and then mix two liquids together, so we know that the molecules are interacting. How do we know what the state of matter is? Sometimes it'll be common sense, which only gets us so far. And sometimes you'll just be told, or you'll have a bunch of reactants in front of you, and you'll just have to make the observation. Hey, this water is liquid. There you go, H2O with an L next to it. Sometimes you'll end up with things like hydrogen gas or oxygen gas. Oxygen gas, liquid oxygen, exists at very, very low temperatures. You have to get the oxygen very, very cold. So if you're doing something at like room temperature, well, you're not going to have hydrogen, liquid hydrogen, or you're not going to have liquid oxygen. It just won't happen at that temperature. So most of the time you'll be told, or it'll be written in there. Very rarely will you actually have to think to figure out what the state of matter is. Usually it'll be there, it'll show up. You won't have to worry about it at all. So in this example above me here, we have hydrogen gas, which is H2. We have oxygen gas, which is O2, and they combine to produce some good old H2O, which is just liquid water. In this case, it's gaseous water, just because of how these things are reacting. So I want to kind of get your brains into the little thinking about why we have these coefficients in front. Why do I need two hydrogen molecules to produce two water molecules? Imagine this for a second. If I only had one hydrogen molecule, so there's just one of these blue guys, and I lost this other one. This one's gone for a second. And then I reacted with oxygen. Well, in order to get H2, so two blue dots, one red dot, if I only had this one, I wouldn't be able to produce two water molecules. I would only be able to produce one. I would be limited by the hydrogen. So when we start talking about balancing, we're really thinking about how are we going to make everything kind of work out so that we end up with things bonding with other things and nothing's getting kind of left over, kind of forgotten about. So that's kind of the general idea. And we'll look at lots of examples of that, and we'll show you how to do that here in a second. All of this came as a result of the law of conservation of mass. And a chemical change means new compounds are created, but no new matter is created. If you start with oxygen, you have to finish with oxygen. You can't start with oxygen and then the oxygen just disappears. If you started with it, you have to finish with it. If you started with hydrogen, you have to finish with hydrogen. The atoms get rearranged, the compounds change, the molecules will change partners, but you can't start with something and not end with it, or you can't start with something and then just end with something completely different. It just doesn't work. So the idea here came from John Dalton, and what he was doing is he realized that the atoms were just getting rearranged. So if we look at the example behind me here, you can see that I start with a CH4, so the black one here is C, and then the white ones are hydrogen, so there's 4 of them. And then I have my two O2s, O2 and O2. So this hydrogen was bonded with the carbon, CH4, but now the carbon is bonded with 2 oxygens. So I started with a carbon, I finished with a carbon. All right, so that changed. I have these oxygens which were bonded with themselves, but now the oxygens are bonded with some some hydrogens. So we've changed the CH4 and the O2, they've reacted to produce CO2 and H2O. And this is actually an example of a combustion reaction. So you guys will be able to recognize these when we finish chapter 6 or unit 6. But this is burning. So if you take a hydrocarbon like methane, which this is, you light it on fire, oxygen in the atmosphere reacts, produces CO2 and H2O. So we'll get really good at these things as we progress. But you can see you start with carbon, you end with carbon. You start with oxygen, you end with oxygen. You start with hydrogen, you end with hydrogen. There's no new elements that magically appeared on one side but not the other. And it'll work like this every single time. So you're not going to magically have some element appear that wasn't there previously. So talking about the law of conservation of mass a little bit further, atoms are neither created or destroyed. They're just going to trade partners, essentially. And this was developed by Antoine and Marie Lavoisier, chemists long time ago. And the important idea here is that the mass of what you start with, if you weighed that, if you actually took a scale and you weighed it, if you started with, let's say, 100 grams of something, you're going to finish with 100 grams of something. That is the law of conservation of mass. And it's a law, so it cannot be violated. There's one instance where it can, but we're not going to talk about that right now. That comes later. So usually when we say the law of conservation of mass is that atoms cannot be created or destroyed by ordinary chemical means. And everything we deal with in chemistry will be by way of ordinary chemical means. All right, so looking at the same examples we just looked at. If I had CH4, that's methane, and I reacted with it some oxygen gas, and I add a little bit of flame to get this reaction to proceed, I'm going to produce CO2 and H2O. So let's, for a second, look at what we're starting with here. I have this CH4 molecule that gives me 1 atom of carbon. I have 4 atoms of hydrogen, and I have 2 atoms of oxygen here, 1 and 2. When I react to produce CO2, I have 1 atom of carbon, I have 2 little blue dots here, 2 hydrogens, and I have 3 oxygens, or 3 red dots. Well, I started with 1 carbon, I ended with 1 carbon. Is it possible that I can start with 4 hydrogens and end with 2 hydrogens? And is it possible that I can start with 2 oxygens and end with 3 oxygens? Hopefully you can recognize that that is impossible. It violates the law of conservation of mass. If I started with 4 hydrogens, I have to end with 4 hydrogens. If I start with 2 oxygens, I have to end with 2 oxygens. I can't start with 2 and then magically create a third one and just add it in there. So this is why we balance chemical equations, and this is where we run into some problems. CH4 and O2, these molecules will always bond this way. They'll always be O2. They'll always be CH4. CO2 and H2O, water. Can water be H3O7? No, water always has to be H2O. So when we form compounds, the compounds only go together certain ways. So if they can only go together certain ways, we can't just say, well, let's not make it H2O, let's make it H3O. Well, that's not water anymore. H3O isn't a naturally occurring sort of stable compound. So we can't just randomly get that extra H there, or H4O, to get all of our hydrogens accounted for. We can't sort of violate how these things combine. So what we do is this. Instead of taking just CH4 and the O2, we can introduce as many molecules as O2 as we want to make it produce the correct amount of water. So this is the exact same equation as what we started with here, but you can see everything balances. I started with 1 carbon here, I end with 1 carbon. I have 1, 2, 3, 4 red dots, I end with 1, 2, 3, 4 red dots. I started with 1, 2, 3, 4 white dots, I end with 1, 2, 3, 4 white dots. And yeah, Abby, you're exactly right. It's an equation, so we can't have 2 equals 7. It just doesn't work. you have to have 1 equals 1, 4 equals 4, 3 equals 3 on either side of the equation. It's exactly like a math equation. So the way we do this is we add coefficients in front, saying, no, we have to start with 2 oxygens in order to end up with CO2 and H2O, and it turns out that we end up with 2 water molecules as a result. So we're going to look at how this works. But the idea is this. You can add more and more molecules to make everything balance out. You can't change how the molecules bond together though. We can't change H2O. It has to be H2O. It can't be H3O. It can't be H5O7. That's not water anymore. We just can't change the compounds. So a few little boring notes here before we look at some examples. The simplest form of chemical equation is called a word equation or a skeleton equation. It doesn't really tell us much. It tells us the elements that are present. So the example here, potassium metal plus oxygen gas gives us potassium oxide. Reactants on the left, products on the right. The arrow is kind of like an equal sign, and that is a very simple equation. So the skeleton equation is kind of the next step. It doesn't show a balanced equation. It just shows you what you're starting with, shows you what you're ending with, but it doesn't balance anything along the way. So if you were to count things on the left and right of a skeleton equation, the left side wouldn't equal the right side. The last step is actually physically balancing these equations, making sure that you start with 4, you end with 4. If you start with 2, you end with 2. And that's what we're actually going to look at today. So you have a simple chemical equation or a simple word equation. You can convert it to a chemical equation, which is called a skeleton equation. And then if you balance it, then you have kind of what we're going to work towards today, a balanced chemical equation. So we'll look at some examples of how to balance, and then there's some questions in your booklet, in your learning guide, which will kind of give you guys some practice at this stuff because it does take a lot of practice to get really good at it. All right, so because of the law of conservation of mass, we can count atoms on one side and they have to be equal to the atoms on the other side, kind of like a math equation. So if we started with a word equation, like methane plus oxygen produces water and carbon dioxide, we can then convert it to a chemical or a skeleton equation by forming the compounds. Methane, CH4. Oxygen is O2, water is H2O, and carbon dioxide is CO2. Now, the notes kind of just say, well, then you just balance. Just go ahead and just balance the sides. And it doesn't really tell you how. So in order to satisfy your notes, to fill in this section of your notes, I'm going to put this stuff up. But don't think that this is just kind of it for balancing. I'm just going to give you it and say, good luck balancing. No, I'm going to show you guys how to do it. We're going to kind of work through it systematically, and we'll do our best to get a good handle on this. But for now, if you just want to fill in the notes, that's great. And when you go back later, you can look at it and it'll hopefully make a little bit more sense. But you can see the example here. If we add a 2 in front of the O2 and a 2 in front of the H2O, it balances. So this is the same equation that we've been looking through throughout the notes. It's the example that we've been using. CH4 plus O2 is H2O and CO2. Well, it doesn't balance. So what we need to do is add some coefficients in front, and we need everything to kind of balance out at the end. So I'm hoping you have that. I don't think there was a ton of stuff to write down. I want to move on to the rules. We'll look at some examples. And we'll call her a day. All right. These are the balancing rules. Now, I don't know if it's funny or not. I'll call it funny. I don't think it's actually funny, but when we start doing these balancing type questions, students will be like, Mr. Borden, I don't understand, can you help me? And they think that because I'm a teacher, that I have some magical way of balancing equations. It doesn't matter if you are just learning to balance equations in grade 10, or you are a chemistry professor at UBC who teaches chemistry every day, all day of their life. The rules for balancing are the same. There's no shortcuts. There's no magical way to do it. The only thing that makes you better at balancing is just practice and being exposed to different types of equations. So if you have a question about balancing these things, I don't just magically have some special teacher way of doing these things. I have to go through the same process as you, and that's just the way it works. So it is kind of funny because students expect me to have some quick way of getting these things done, but there just isn't. Everyone does them the same way. There's lots of different ways to do them. You need to figure out a way that works best for you. I'll give you one method that I think is the easiest, and you can use it or not. You haven't balanced anything yet, so this trial and error is a way to do this. You can just guess and just work through it and hope it works. And if it doesn't, you do it again until it works. And this can be a way of doing these things. And sometimes it'll work, and sometimes it'll take way longer. So when we say trial and error will work, but it's inefficient, yeah, you can try to balance these things several different ways. If it doesn't work, then what do you do? The rules that we'll come up with are balance compounds first. If you have CO2 on one side of your equation, and on the other side of the arrow you have another CO2, balance those things as a group. Balance compounds on either side first. And then if you have sort of compounds, balance them one at a time. Don't try to balance CO2s, then PO4s or whatever. You can only add coefficients. So you can only add numbers in front. You can't change the subscripts behind, because that would be like changing H2O into H3O or H5O. You can't do that. It's water. It's H2O. You can't change the subscripts. You can only add coefficients in front. These last couple rules don't always come into play, but sometimes they do. So if you have something by itself, usually an H or an O, if they're just kind of hanging out by themselves, you're going to want to balance those last. And if you have polyatomics, like the example here is SO4, if you have a polyatomic on either side, you want to balance those as a group, which will make your life easier as well. When you get to the end, you think you're done, go back and double check. Now, having said all of that, it doesn't really make sense until we actually go through the process. So I'm thinking it's about time we started to try to balance a few equations. We'll start easy, we'll get a little tougher, and then see how you guys do. Now, when I do these things, sorry this second one didn't work out here above my head. The vertical line should be at the arrow. That was just a typo sort of thing. So your notes say, balance the following. Now, it doesn't say how to balance them. It just says, go ahead and balance them. But when I balance these, I always do them the same way, and I draw a T-chart. And I'll show you what that looks like. And we'll do these 3 examples, and then I'll give you guys an opportunity to do some examples. So I'm going to jump into Notepad here so I can do these. This is FEBR2, FEBR3. I believe that's the same. Yes. All right. So I said draw a T-chart. And there's my T in red. And what I'm going to do is I'm going to write down the elements on the left side here. And remember, these are my reactants. And these are my products. So my reactants, what am I starting with? Well, I have an Fe, which is iron, and I have a Br. And then over here, I have an Fe and a Br. Now remember, the law of conservation of mass says if I start with iron, I have to end with it. And if I start with bromine, I have to end with it. So my reactants and my products will always be the same, 100% of the time, no exceptions. Now I need to count how many there are. So how many irons do I have on my reactant side? Well, I'm looking up here and I see that I have an Fe, nothing written next to it, so I know I have 1. And then I'll do the same thing for bromine. I have Br with a little 2 next to it, so I have 2 bromines. All right, that's a good start. Now I'm going to count the other side. Over here I have 1 iron, even though there's nothing written behind it. There's 1 there. And then I have 3 bromines. So, do I have a problem here? Is this thing balanced or not? Well, I started with 1 iron and I've ended with 1. So my irons are okay. I have balanced these things. That's good. Started with 1, ended with 1. My bromines, on the other hand, not looking so good. I can't start with 2 and end with 3. That violates the law of conservation of mass. I can't start with 2 of something and 1 magically appears and I end up with 3 of them. So what I need to do is balance. And the way I do that is I can only add coefficients in front. So I will always draw little spaces in front of all of my reactants and products. And what I can do is I can add numbers on either side to make this balance. Okay, so my irons are balanced. I don't have to worry about those, but my bromines aren't. So I can put numbers in front here. If there's no number there, it's kind of like math, there's assumed to be a 1. I don't have to write 1s in. So what I'm going to do is add more than 1. So I have 3 bromines on the right side, and I need 3 bromines on the left side. Is there anything I can put in front of bromine to end up with 3? Well, imagine this for a second. What if I put a 3 here? What does that do? Well, that means I have 3 groups of 2. So that actually changes this to a 6. And that doesn't get me any further ahead. So I can't put a 3 here because that means I have 6 bromines. Is there any number I can put in front, which means I'm multiplying by the 2 behind, that'll give me 6? Or sorry, that'll give me 3. There's nothing I can multiply by 2 to give me 3. I can't put in decimals. I can't put in 1.5. I have to put in whole numbers. So I'm running into a bit of a problem, even though this is my first example. And that problem is this. I can't get 3 on this side. It just is impossible. So 1 and 5 doesn't work because it's not an integer. So what I have to do is this. I think a little bit further ahead. Well, all right, I can't do 3, but what if I put a 3 in here, and then 3 times 2 changes this to a 6? Is there a way to get a 6 over here now? Well, sure. If I put a 2 in front here, that means I have 2 of this FeBr3 group. That changes that to a 6. So I have a 6 and a 6, and that's good. Now, some of you who are a step ahead of me are thinking, well, Mr. Borden, you silly guy, you put a 2 in front over here, and that changes the iron to 2 now, as well as changing this to a 6. So you've unbalanced the irons. So what I need to do to remedy that is I need to go back and put a 2 over here now. And that changes that to 2. And everyone's now happy. So, is that the best example to start with? Probably not. But that's the one the book chose, or the course chose. So, we'll go with that. So, this should be a 2, a 3, and a 2 in each of those coefficients. Yeah, it's confusing, I know. I promised we'll do a bunch of examples, and these aren't simple examples to begin with, but just kind of the way the course had it laid out. Let's do this next one, and we'll see how we do on it. Same process, T-chart. Now, if your polyatomic ions are the same on both sides of your equation, you can balance them as a group. So what do I mean by that? Well, my reactants over here, I have this NO2 group, and in my products, I also have an NO2 group. And I have a PO4 group on this side, and I have a PO4 group on this side. So I can balance these as groups. I also have some other elements. So I have SN, which is tin. I have potassium. I have this NO2 group, and I have a PO4 group. If I start with, pardon me, tin, potassium, NO2, and PO4, I'm going to end with tin, potassium, NO2, and PO4. If I start with it, I have to end with it. There's no way around it. Law of conservation of mass says if you have it to begin with, you must have it to end with. What I'm also going to do is add some little blanks in front here so I can write my coefficients in. And then I'm going to count. How many SNs do I start with? Well, I have one group to start. How many potassiums do I have on the reactant side? I have a 3. I have 4 groups of NO2, and I have 1 group of PO4. So those are my reactants. And then I have my products. How many tins do I have here? I have 3. I have 1 potassium, 1 group of NO2, and 4 groups of PO4. All right, now just like that other one was a really tricky example, this one is also quite evil as well, but we'll just go with it. We'll do the 3 examples that show up here in the notes, and then I'll go to the learning guide and I'll pick some easy ones to go through. But just so you guys have these ones done, we'll do them. All right, I'm going to balance SN or tin first. Why did I pick that one? Well, it's an element, it's on both sides. We're going to have to balance it. So here we go. On my reactant side, I have 1 group of SN. On my product side, I have 3. So I can't start with 1 and end with 3. So what I'm going to do is I'm going to find SN over here, and I'm going to put a 3 in front of it, which gives me 3 tins. But what else does it do? It changes this NO2 group. Before I had 4 groups of it, but now I have 3 times 4 groups of it. So now I have 12 groups of it. All right, so SN's balanced. Let's look at NO2 here next. Now I have 12 on this side. I need to have 12 on this side. So in front of the KNO2, I can't just put a bracket and then put a little 12 behind it. That actually changes the compound, and I can't do that because K and NO2 only go together in one way. So I'm going to get rid of those brackets. I can't add brackets. The only thing I can do is add numbers in front. So if I have 12 on one side, I have to have 12 on the other. So I write 12 out front here. That changes this to a 12. But it also changes my potassiums, or my K. I had 1, but now I have a 12 in front. So my potassium's gone from 1 to 12. Okay, if I look next, I have 3 tins. I have 3 tins. That's good. My NO2s are at 12. My NO2s are at 12. I have this potassium to deal with. I started with 3, and now I'm ending with 12. So I need to address that. Now, to make this 3 into a 12, what do I need to do? If I put a 4 here, I get 4 times 3 is 12. But that also changes my PO4 group to 4 groups of PO4. No worries, Taylor. Thanks for showing up. So my potassiums are good, 12 and 12. My PO4, I started with 4, now I'm ending with 4. So that one actually worked out kind of along the way, just kind of lucked into working out. I didn't even have to actually think about it, it just kind of worked out. So again, that's a tricky example of balancing, but now you have it done. So if you're kind of getting the hang of it, good. You're going to see lots and lots of these. We'll start with really basic ones in the learning guide. We'll work our way up to more complicated ones. Let's do this last one and then we'll look at a few from the learning guide. And I will say this is kind of like the math, because when you see me do it, you're like, oh, that's pretty straightforward. You just add a couple numbers here and there and away you go. Well, yeah, it's easy to watch somebody do it, but when you need to do it yourself, it can get a little bit more difficult. So we'll do this last one and then we'll go from there. It might be worthwhile for you guys to just watch these and then not actually try to write it down, like crossing it off and everything that I've been doing, just because you're not going to understand where the, sorry, get out of the way. You're not going to understand where the crossing is coming off. And what I would recommend is you guys can go back and maybe rewatch this, or once you do a few examples that are a little bit more straightforward, then you can kind of go from there. If you can just pick up little things here and there, that'd be good. So maybe just this last one's going to be a tricky one again. So maybe just watch the last one. Don't even bother writing it down. You can just watch me go through it. And then we'll do some out of the learning guide that you guys can actually write down. We'll start with some easy ones. All right, so I'm going to draw my T-chart in red. Now, this is an example of a combustion reaction, and these are the hardest to balance. So what do I start with? I start with a carbon, a hydrogen, and an oxygen. If I start with it, I have to end with it. So if I start with a carbon, I must end with a carbon. If I start with a hydrogen, I must end with a hydrogen. If I start with an oxygen, I must end with an oxygen. How many carbons do I have to start? Well, carbon shows up in one spot, and there are 2 of them. Hydrogen shows up in one spot, there are 6 of them, and oxygen shows up in one spot, there are 2 of them. Carbon on the right side shows up in one spot, and I have 1. Hydrogen shows up in one spot, and I have 2. And oxygen actually shows up in 2 spots. So I have 2 here, and an additional 1 over here. This is what makes balancing combustion reactions so difficult. It's because you have oxygen showing up in more than one spot. So you actually end up with 3 oxygens on the product side. All right, let's see how we can do this. I am going to draw some spots in front to add my coefficients. And let's start with the carbons. I start with 2 carbons on the left, or my reactant side. I end with 1. That's not going to work. So what I'm going to do is I'm going to put a 2 here. That gives me 2 carbons. That also changes my oxygens to 2 and 2, plus another 1. So my oxygens go from 3 to 5. Now this is why combustion reactions are so difficult. I have an odd number of oxygens here. There's nothing I can put in front of my oxygen here to make it odd. I'm multiplying by 2. I can't get an odd number if I'm multiplying by 2. It's impossible. So that's why this is so tricky. Let's go to balance our carbons and then, or our hydrogens, sorry, and then we'll see if maybe it works out a little bit nicer for us. So on my reactant side, I have 6 hydrogens. On my product side, I have 2 hydrogens. So that's not going to work. If I have 6 on my reactants, I need 6 over here. So I'm going to put in a 3. And 3 times 2 is going to give me 6. And my oxygens, I'm going to have 3 here, and then I'm going to have another 4 here. So my oxygens aren't 5. They're 3 and 4, which gives me 7. So I can't put anything in front of this. My carbons are balanced at 2 and 2. My hydrogens are balanced at 6 and 6. I cannot put anything in front of this oxygen to get 7. 2 times 3.5 gives me 7, but I can't multiply by 3.5. So this is why combustion reactions are hard, and this is kind of the trick that we do. The trick is this. I hate to give you the trick already because you haven't even done any of these yet, but anyways, the trick is this. In order to get rid of the odd number of oxygens here, what I want to do is I just want to double everything. And what I mean by doubling everything is I'm going to put a 2 here. Let's not think of it that way. Let's think of it as just doubling this guy. So I'm going to put a 6 there. And by doubling it, I end up with an even number of oxygens over here. So let's see what the fallout of that is. So I have 6 plus another 2 is 4, so I have 10 oxygens now. And 6 times 2 hydrogens is 12 hydrogens. So I'm going to go back and put a 2 here, which gives me 12 hydrogens and 4 carbons. Now, this 2 isn't good enough anymore, so I need to go back and change that to a 4, so my carbons balance. So I have